to start a unit talking about logarithms. Now, we did learn about this in Algebra 2, but I believe it was second semester towards the end of the semester, so who knows if you were still paying attention at that point. But this is a pretty important function for us, especially in this unit. We studied exponential functions at the beginning of the unit, and there was a bunch of problems in that unit where I said we didn't quite have the math skills yet to solve it by hand, so we used technology to do it. But it was really cumbersome on our pieces of technology to zoom out to like 1,500 or 15 million. So at the end of this unit, we'll be able to solve those problems by hand. We're not going to get into that today. We're just going to start at the beginning of logarithms. And really, we're going to go back to the idea of inverse operations. So every operation has exactly one inverse or opposite operation. We've learned these inverse operations since forever. So what is the inverse of addition? Subtraction. So to solve for x, you would subtract. What's the inverse of multiplication? Division. To solve, let me write subtraction where it actually fits in that box. That's just unnecessary. What's the inverse of cubing something? Ooh, but it's a cube though. Cube root. So squares would be square root, cube would be cube root. Or any of the roots to undo the power. But here's the thing. If I have something that is an exponential function, the power is not a number anymore. The power is a letter. We have not learned how to undo that. Preview, it's going to be a logarithm. So we've learned about these exponential functions, but to solve them by hand, we would need to create an inverse operation for exponentiation, or taking x in the exponent. So here's our big idea for today. Just as we can write rational numbers in decimal form and in fraction form, so like 0.5 is the same as 1/2, we can also write equations in two forms. They can either be in exponential form or in logarithmic. These forms create equivalent statements that represent the same claim. Just like 0.5 and 1/2 are the same number, an equation written in exponential form and an equation written in logarithmic form is an equivalent expression or an equivalent equation. Essentially, all we are doing is rewriting these equations. Wow, I'm using the worst kind of handwriting today. Let me write that where it's a little bit easier to read. Sorry about that. That's a little bit easier to read. So let's look at how to switch these from exponential to logarithmic form. If we notice, we have three letters in an exponential form. You have your b, your base. You have your exponent, most of the time that's x. And you have your equals to number, or what it evaluates to. We're going to take those same letters and rearrange them to write this exponential form in logarithmic form. Here's how you do it. The logarithm has a subscript. That's called the base of the logarithm. That's the b, that's the base. The base never changes. The base with the exponent becomes the base of the logarithm. But after that, the equal to number and the exponent just switch positions. So we call this the log loop. The base never changes, but these letters are going to loop around the equal sign to change it from exponential to logarithmic form. We call that the log loop. So the two notes I want to have you write for yourself is, number one, that the base never changes. Whatever number is the base of the exponential is the base of the logarithm, and vice versa. The base of the logarithm is the base of the exponential, or the number with an exponent. The other thing you do is you just loop, so we're going to call that the log loop. You log loop the A and the C. They switch places. So we're just writing them back and forth between these two forms, the same way I could ask you to take a decimal and change it to a fraction, or a fraction and change it to a decimal. There is two notations here that we need to make sure we remember from when we learned this the first time. If the base of a logarithmic expression is 10, it's so common and it's used so often that we just straight up call this the common logarithm, and we write it without a base showing. Kind of like how, bless you, how 1 is so common as an exponent, we just don't write it anymore. Or 2 for an index, like a square root, is so common we don't write it. That's how a common logarithm works. So if you just see the letters log with no base showing, the base is 10. It's just hidden because it's so common, we got tired of writing it, so we just say if there's nothing there, it's 10. The other super common logarithm is called a natural logarithm. The natural logarithm has a base of e. E is your natural number, Euler's number. So if you see the natural logarithm, which is written like this, ln of x, it's ln instead of nl because in the language that this math was created in, you put the adjective before the verb. So, or adjective after the noun. I know English words. So natural logarithm is ln. Notice on your calculator screen for 1 second. Do you see a button for logarithm and a button for natural logarithm? Ooh, you should. There's a whole button for them. On the left side in the black buttons, there is a log button and there is a natural log button. You can only use these two buttons if you are taking the common logarithm and the natural logarithm. If you're doing any sort of other logarithm, I will tell you the steps later. But that is for regular log, common log, and natural log. Sound good? Yes. Cool. Before we get into evaluating functions, let's just make sure we know how to rewrite expressions from logarithmic to exponential form. So in this example 1, this is in exponential form because there's an exponent. I want to rewrite it in logarithmic form. So a couple things. The base never changes. The other two numbers are going to flip-flop. I'm only going to highlight the base from here on out because that's the one that's important. So we would change this to a logarithm by writing log for log and giving log a subscript of 3. Notice it is not big 3, it's a little 3 subscript. Then I'm going to loop the other two numbers. So I would say log base 3 of 9 is equal to 2. Log base 3 of 9 is equal to 2. That's how you pronounce that. Does that make sense? That's as easy as it gets. Can I have you guys try B, C, and D already? I think we're ready to try some on our own. So for B, what is the base? 10. So I would say log with a base of 10, and then I loop the other two numbers. So log base 10 of y is equal to x. Now this wouldn't be an answer choice because that base is 10, and we can actually simplify the way we write it, since it's a common logarithm, to the log of y equal to x. That was what you would see as an answer choice. If it is a common logarithm, write it as a common logarithm. For part C, what is the base? R. So r raised to the t power is equal to w is equivalent to, if we flip-flop these and say logarithm with a base r of w is equal to t. And then the last one, what's the base for D? E, very good. Okay, so E is my base. That means my base is on the opposite side of the equal sign. Don't worry. We write log with a base of E. Ooh, spidey senses are tingling. We'll fix that in a second. And we're still going to flip-flop the x and the y. But notice I put the base on the left side this time. So when I flip-flop the exponent and the equal to number, the evaluated number, I actually have to make sure I flip-flop which side they go on for the logarithm itself. So the y should go with the log because it's with the base now. And the 3x should go to be the equal to number, even though I rewrote it the opposite way. Now, of course, your spidey senses should be tingling because log with a base of e, how do I write that? Yeah, natural log of y is equal to x. I know it's tempting to say, it is tempting to say ln, and you can say that to yourself, but we're going to say out loud natural log. So natural log of y is equal to 3x is how we would write that. Okay, cool. So we went from exponential form to logarithmic form. Base stays the same, we log loop. What if I want you to go the other way? I have all of these expressions, and I want you to rewrite them in exponential form. But the rules are still the same. The base never changes. So the base here is 7. That's going to become my big base. And then I loop the other two numbers or letters, which means this is going to be 7 squared equal to x. Base stays the same. We loop the others. That make sense? Let's have you try B, C, and D again on this row, switching from logarithmic to exponential form. For B, what is the base? 3. And then we're going to loop the others. So when we loop the others, the letter that should go next to the 3 now is x, and then it should be equal to y. For part C, what is the base? 10. I don't see it, and I do see log, so I know that that base is going to be 10 since that's my common logarithm. And then I loop the other two. This would be 10 squared equal to y. And then last but not least, what is the base of D? E. That is my natural logarithm, which means my base is e, and then I loop the other two. So this is e to the 4th power equal to c. Now remember, we're writing equivalent equations, which means all of these things must actually be equal to each other. So we can use the logarithmic idea of log looping to evaluate logarithms, which we're going to do on the next page, so go ahead and flip over your notes. Without using a calculator, we're going to evaluate some logarithms. Because first of all, how do you even type some of these logs into a calculator? You can't type that one into a calculator because it has a base of 2. The only buttons you have on your calculator are base 10 and base e. But we can use the idea of power families to go back and what words am I trying to say? Let me just read the sentence off the paper. Oof. Sometimes we can evaluate log expressions without the use of a calculator by utilizing its equivalent expression or exponential form and thinking about power families / exponent rules. Now we did that GimKit when we came in, so some of these should be pretty fresh for us. To evaluate without using a calculator, we're going to take log base 2 of 8 and we're going to set it equal to x because we're looking for what it's equal to. Old school, you could have put a question mark right there. You're like, what is this equal to? Well, now that I see it written like this, I can log loop it. The base is going to be 2, and I'm going to loop the other two things. So I say 2 to the x equal to 8. Well, this problem is just asking me, what do I have to raise 2 to get 8? But if you think about your power families, isn't 2 to the 3rd power the same as 8? 2 times 2 is 4 times 2 is 8. And if these two expressions are equal to each other, what is the value of x? 3. Because if the bases are the same, the exponents must be equal to each other. So what I want you to do in these problems is I want you to take this number that it's equal to, your evaluated number, and rewrite it as a base that matches the exponent side. 8 can be written as 2 to the 3rd power. Therefore, x is equal to 3. So log base 2 of 8 is 3. We've evaluated the logarithm. Let's see B again so you can see this one more time. So we're evaluating log base 5 of 25. We want to know what that is equal to. So we're like, well, it's equal to something. We're going to call that x. That's our placeholder. That's our variable. We're solving for x. But my base here is 5. So this would be 5 raised to the x power equal to 25. Can I rewrite 25 as a base of 5 to some power? Yeah, it's 5 to what power? 5 to the 2nd power. So what is x equal to? 2. So log base 5 of 25 is equal to 2. We've evaluated the logarithm. Can I give you some time to practice the rest of these? I know there's a whole bunch on this row, but I want to see what we're thinking before I just give you some more information here. So I'll give you more than just like a minute, maybe like 2 or 3 minutes. See if you can get all the way through H completed. Okay, I'm hearing some great conversations, but let me come to the rescue on some of these. For part C, the base is 2. So if I rewrote this as an exponential, I would have a base of 2 raised to the x power equal to 32. Well, I recognize 32 as part of the 2 power family because it is 2 to what power? 5. 2 to the 5th power is the same as 32, which tells me that x is equal to 5. So log base 2 of 32 is equal to 5. In part D, ooh, sneaky, what's the base here? 10. So we're saying, that's not a highlighter. We're saying 10 raised to some power, which we don't know, is going to be equal to 100. Is 100 part of the 10 power family? Yes, it's 10 to what power? 2. Those of you who had the crazy ones on the Gim kit that was like 10 to the 6, do you know the trick about 10s to the powers? It's the number of zeros. So 10 squared is 100 because there are 2 zeros. So 1 million is 6 zeros, so 10 to the 6 is 1 million. Yeah. So we know here, sorry to digress about powers of 10, but that's a fun fact for you. The next row starts with log base 16 of 4. We want to know what this would evaluate to. Well, the base is 16. Okay. We have 16 raised to some power equal to 4. Again, I want to write the equal to number, the evaluated number here, as a base of 16. How do I do that? Well, isn't 4 16 squared? But if I wanted to work the other direction, this would be 16 to what power? 1/2, like the square root of 16. Square roots are 1/2 powers, which means that x is equal to 1/2 here. Did we get that one? Okay, I heard great conversation about this next one. What's the base? 3. So we have a base of 3. And we're going to raise that base of 3 to the x power and set it equal to 1. And then how do you write 1 as a base of 3? Anything to the 0 power is equal to what? 1. So x is equal to 0. We forgot about that exponent rule around the room a little bit. That's okay. Remember it now. How about letter G? What's the base? 10. Again, common logarithm has a base of 10. We have 10 raised to the x power equal to 10. So what is x? It's 1, because anything without an exponent showing has an exponent of 1. And last but not least, we have h. What's the base of h? 6. We're going to have 6 raised to some power, because that's what the logarithm is equal to 1 over 36. Now, if you didn't see this, I recognize 36 as part of the 6 power family. The problem is, if I put that down, it's still in the denominator. How do I get that out of the denominator? I heard it. Make it negative. So what is x equal to? -2. If these were not necessarily clear for you, that means we got to get our power families better in our brains. Okay, get your powers of 2s, your powers of like all of the single digit numbers really pretty fresh, up to like 3 or 4. Now, I kind of lied to you earlier, but I did it on purpose. If you look at example 4, it literally starts off by saying, use a calculator to evaluate the following expressions. Now, the first 2, you're going to be like, great, we have a whole button for that, log of 9. So we go to our calculator, you press log, you press 9, you press enter. It's going to give you a decimal, because most of the time logarithms do not return nice, pretty numbers. Log of 9, if you trust me, would be approximately equal to 0.9542. I'm using 4 decimals because it specifically asks me to use 4 decimals. Log of 6,125, again, on your calculator, you press log, you press 6125, you press enter. And it should return to you a number. If you're doing it right, it should return to you approximately 3.7871. Do y'all agree with me? Okay, here's where I lied to you. Look at number C and D. What's different about these? They have a base that's not 10 and a base that's not E. Oops. You actually can type these into the calculator. There used to be a whole formula we had to use for this, and I believe I'm going to show you it later in case the AP test asks you to look at a change of base formula. But the calculators have gotten smarter since my day, and now you can actually type these in. So write this down because it's not printed on your paper anywhere. To find this in the calculator, you're going to press Math, and then you're going to toggle over to this, or sorry, not toggle over. You're going to go down to option number A, which says log base. Okay, so in the math menu, there is an option that says log base. You can't see it, you have to scroll down to it, but it straight up gives you a logarithm that has a space for a base and a space for an evaluated number. So go into your calculator, you press Math, scroll down to A, or press A, and then you can type this in. I'll give you a second to find it. Does anyone need me to show you? No? Okay, great. If you do this correctly, you should get approximately 3.3219. Yes? Ooh. So like I said, there is a function on your calculator now for this. I believe in one of the later notes I will give you the actual change of base formula in case we see it. But that change of base formula would allow you to do this on any calculator, even if it's one of these that got disabled. But for now, we'll use Math and then log base to evaluate. Now, I want to make a point on this of why it's important to know how to evaluate using the calculator versus by hand. Because if we were looking at letter C, and we solved it the way we did the ones on top. So this was log base 2 of 10 equal to x. We would log loop it. This would be 2 to the x equal to 10. Is there any way to write 10 as some sort of power family of 2? No, it's not one of the powers of 2. This is going to be one of the problems where you have to use the calculator to solve it. The ones that ask you to do it without a calculator are always going to have the numbers be in the power families. Otherwise, we'll tell you you can use your calculator. Does that make sense? Okay. Because there's like no way you would know that 2 to the 3.3219 etica, more decimals, is equal to 10. Like there's no way. Now, we're going to continue to talk about this over and over again, but we're going to talk about why logarithms are useful, especially when it comes to data analysis. And this is one of those topics that, okay, my dad's an engineer, and he like loves to nerd out about engineering things. And my whole life, I've kind of tuned him out. And when I was learning about this stuff, he looked at it and he was like, okay, you're going to have to let me nerd out for a second and tell you why this is so helpful. So if you are interested in any sort of engineering, my dad's a petroleum engineer, so petroleum engineering, if you're interested in that, he uses a logarithmic scale, which is what we're going to learn about literally every day. So this is actually something that, depending on what you do with your life, may be super duper important for you to understand. But what's useful about logarithms, and why my dad went bananas about it, is because when you look at exponential data, like this graph down here, okay, exponential data gets big really, really fast. But for a while down here, for us to be able to see this data point, where it got really big, we have to minimize what we can see about these beginning data points. So this first data point looks like it's at like 0, 0, which is really misleading when it comes to reading exponential graphs. So what logarithms allow us to do is take an exponential graph and graph it on what's called a logarithmic scale so that we can see more information about what happens early in the data while also seeing what happens later in the data at the same time. So in this example here, this is showing the population of English Americans in the current United States since the year 1620, the population of the United States. Obviously, we've grown a lot, but we didn't start at 0 in 1620. There were people living here, but it looks like we're at 0. So this graph here shows us just the regular exponential graph where we go from 0 to 7 million in the population. Again, really hard to tell what's happening in these early years. But if we use what's called a logarithmic scale, we're going to highlight this word right here, logarithmic scale with a base of 10, that's my common logarithm, we can actually see more information about what's happening early. These data points are all the same. So if you look, we still have at the year, what is that, 1820, because it's 200 years after 1620. It's up here at 7 million. At 1820, this is still showing me that it is approximately at 7 million. This is 6 million, 10 to the 6. This is 1 million. This is 10 million. So 7 million is somewhere in between, which is why this data point is in between. That has not changed. But what's, again, helpful is that this data point that looks like there was 0 people living here in 1620 gets translated up to this data point. In 1620, there was approximately, less than 1,000 but more than 100 people living in the United States. English Americans, so immigrants, not the native people of America because they've been here forever. So the difference here in this log scale is that I get to see this information much easier than when I see it here, because this doesn't look like anything. Looks like there's one person living in the United States. Not true. So we're going to continue to work with these log scales throughout this unit. If you look at the back page here, we're going to add some more data points to the same log scale. So this is the same picture from the front. It's still talking about those English Americans in the current United States, starting in the year 1620. And ending in the year 1880. That's what this has been extended to. So we're going to plot 3 additional data points on our graph. This is a log scale. Take your highlighter right now, and I want you to just aggressively highlight this side right here. These are not counting by 1. These are not showing you 1 million, 2 million, 3 million, 4 million. We talked about power families earlier. 10 to the 1 power is what? 10. 10 to the 2 power is what? 100. The next is? Then? And then? Okay, we get it. 1 million and then 10 million. We're adding zeros each time. So if we want to plot some additional population points in here, the year 1840 is 220 years after we started counting, because we started in 1620. And the output, or the population, is 17,609,453. 17 million is more than 10 to the 7th, because 10 to the 7th is 10 million. So we're going to go to 220, and we're going to plot ourselves a point a little bit above the 10 million part right there. If you're like, how did you decide that particular point? That's a great question. Here's what I did on my notes that I realized I didn't do just now. Let's take the logarithm of this number right here. The common logarithm, because we're working in base 10 on our side, so we can just press the log button on our calculator. But go ahead and put log of that 17,069,453 in your calculator. You're going to get a tiny small number compared to 17 million. What did you get when you do that? $7.2322, yeah? So I'm like 7 units up and a little bit more. So if I look at what I've plotted, this is 1, 2, 3, 4, 5, 6, 7, and a little bit more. That's where I'm trying to plot the point. Yes? Okay. What about the next one? If I wanted to plot 31,443,321 for the 1860, remember 1860 is 240 years after we started counting. We started counting in 1620 by this graph. We're going to take the log of this number, and we're going to plot that point. What is the log of 31,443,321? Do you get 7.4975? Fabulous. So 7.5-ish. So we should be halfway between 10 to the 7th and 10 to the 8th, which I know is not on our screen, but we're just going to do our best and plot that point for ourselves. Let's do the same for 1880. Remember, 1880 is 260 years after we started counting in this graph, because we started graphing these things in 1620. We're going to, again, take the logarithm of this number, and we're going to plot it on this screen. When you take the logarithm of that number, you should get 7.7006 approximately. So again, we're pretty high up on the 10 to the 7th point well, maybe not that high, more like, yeah, that looks good to me. Now I'm going to add one more. It's not written on your paper, but I think it's helpful to see. Let's do the year, or let me rephrase. Let's pretend that the population gets to be 150,000 million, what? 150 million people in some year. We won't have to put a year. But if we were to take the log of this number, what would be the log of 150 million? It's a lot of zeros. What'd you get? Yeah, 8.1761. Oh, so now we're in above 8. So if we were to plot this population, we'd have to look on our graph for an additional section, 10 to the 8th. And your orange dot would be above the 10 to the 8th moment, whatever year this is, above that 10 to the 8th. Now, some comments I'm expecting you to make, and it's a truly okay comment. Wow, this was hard to graph because there were no lines written across this screen. I completely agree. Let me introduce you to what's called a semi-log plot. If you look down at the bottom of your notes, a common type of graph with a logarithmically scaled vertical axis is called a semi-log plot. This type of plot is bound to appear on your AP Pre-Calculus exam. It is also the exact thing that my dad has nerded out about every time I talk about the fact that we're learning semi-log plots. This is very applicable to a lot of things that study things that grow exponentially. Now on this graph, if we kind of tie it into what the other one looked like, this value right here is 10 to the 1. What's this value right here? 10 to the 2. What's this value right here? Okay, so we're still doing this graph with the different values or powers of 10, but if you notice, now I have lines floating across my screen. They are not evenly matched. They are not evenly spread out, but there are 10 in every section. So I have 0, and then I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 lines. There are 10 lines here. There are 10 lines here. Those are going to represent the 10s in between them. Meaning, if I were to plot the point 1, 20, here's 1, here's 10, so 20 is right here. Because it's 1 more than 10. So that right there is A. If I were to plot 2, 300, I need to be above the 100 by how many lines? By 3 lines, because it's 300. So I go 2, here's the 100 line, but I'm going to go up 3. 1, 2, 3. This is 2, 300. That's B. Let me see what you think on C, D, and E. Plot those points on this semi-log plot. Maybe in pencil, so if you do it wrong, we can erase. Okay, for part C, it says 3, 2. Seems so simple. So we're going to go to 3, and we're going to go in the single digit section up 2. We should have it right here. 3, 2. How'd we do on that one? For D, is 4, 15. Okay, so 15 has to be above the 10 spot, but less than 20. So this is 10, this is 20, which means this right here is going to be 15. Halfway in between 10 and 20. So for E, which is 5, 350, it's going to be above the 100 by 3, but halfway between the 300 and the 400. So this is 100, 200, 300, 400, which means this is going to be in between them. Just do your best because I know my marker is like bigger than the entire space, but that is letter E. 5, 350, halfway between 300 and 400. Yeah. Okay, my bad. Princey totally pointed out that I plotted one of these wrong. I'm so sorry if you did it in pen. This was wrong. 2, 300 should be this. Oh, wrong color, Miss Quigley. This should be this point right here. Because this is 100, 200, this is 300. I apologize for that. Thank you for keeping me honest. Did I do the same thing on C? LOL, I'm also wrong on C. Okay, oh, it didn't erase. Y'all, when I'm being crazy, call me out. So if 1 is the bottom line, that means this is 2. Y'all should have told me. What do you mean? Tell me when I'm crazy. So sorry. So sorry.